So this video is on isotopes. It's just a preview of what we're going to be talking about in class on Wednesday. So please take notes and follow along to save us some time in class on Wednesday so we can do an activity. If you want to follow along in your textbook, we're on page 100. It talks about isotopes. We're going to be looking at an animation as well. So an isotope is basically, if we write down the definition, it's atoms with the same number of protons but different numbers of neutrons. So this kind of goes against what Dalton proposed. He proposed that atoms were made up of these indivisible particles, and that these indivisible particles were all identical for the same element. We now know that these particles are made up of atoms are made up of subatomic particles, including protons and neutrons, and then surrounding the atom in that kind of clouded space, we have the electron. We also now know that all atoms of the same element are not the same. They do always have to have the same number of protons, right? This determines the element. But in nature, we can have the same element, but the atoms would be different. So what's going to vary? Well, the number of neutrons is going to vary. And we're going to take a look at that in an animation real quickly. So if we take a look at this animation, we start with the hydrogen atom here. We have hydrogen 1. And this is a stable atom. And the relative abundance of this isotope in nature is 99.9885%. Other hydrogen isotopes are just shown by that little sliver in the pie chart. So this is the most abundant and stable atom of hydrogen that we can create. It's got one proton and one electron in the electron cloud that surrounds it. Now, if I add a neutron, am I going to change the type of atom? No, because it still has one proton. But now I've made hydrogen 2. Notice this number after the name hydrogen, that's its mass number. So I now have hydrogen 2. It has a neutron and a proton, which give it a 2 atomic mass unit, and it has one electron still floating around. I can add another neutron. Now you'll notice that the nucleus is starting to kind of wiggle around. That's because this is an unstable isotope. It is not going to last very long. It will decay to become stable. And the same thing is going to happen if I add more and more neutrons. I have this unstable atom, and that's 0% in nature. It will not stay put. It'll break apart and decay. So I've got 2 of these stable hydrogen isotopes. You can do the same thing if you want to go to the website and you can kind of look at the different atoms. Notice boron 11 here is stable. If I take away a neutron, it's stable. If I take away another neutron, though, it's not stable. So boron 10 is 19.9% of all the boron atoms in nature, and boron 11 is 80.1%. Boron 12 or boron 9 are unstable, 0% of them are in nature. So there are different versions of atoms in nature, and we call those different versions of these atoms isotopes because they have different numbers of neutrons. Okay, they are going to have this kind of relative abundance, and usually no matter where a sample of an element is obtained, the relative abundance of each isotope where a sample is going to be, or for a sample, is going to be constant. So your book kind of talks about, like, if you have a banana, I'll draw a banana here. Oh, you get to look at my lovely drawings. There's a banana. There's potassium in that banana, right? Everybody tells you to eat bananas because there's potassium. Well, there's different types of potassium in that banana. You're going to have one potassium. Okay, K is a symbol for potassium. The mass of one of those potassium ions is going to be, or atoms, is going to be potassium 39. And it has an atomic number of 19. Okay, so it's mass number 9. Another potassium in that banana is going to have a mass of 40. And another potassium, type of potassium atom is going to have a mass of 41. They all have the same atomic number, but they just have different mass numbers. And the relative abundance of these different isotopes is going to be the same from one banana to the next. So for potassium 39, it's going to have how many neutrons and how many protons? Well, it has 19 protons, and it's going to have 39 minus 19, 20 neutrons. Okay, and that one is 93.25% of all the potassium. So 93.25% of the potassium in this banana is going to be potassium 39. Okay. I'll shade it in a little bit more. So that's potassium 39. Now if I look at my second isotope of potassium, how many protons does it have? It has 19 because it's still potassium, but its mass number is 20. So 40, sorry. So 40 minus 19 is going to give you 21 neutrons. Well, how relatively abundant is that isotope? It is 0. Let's do another color. 0.0117%. So tiny little sliver is potassium 40. And potassium 41 is going to have how many protons and how many neutrons? Well, again, it has 19 protons because it's potassium, and if it has 41 for its mass number, 41 minus 19, it's going to have 22. And that is going to be approximately 6.7302% of all the potassium ions. I keep saying ions, sorry, atoms. That didn't work very well. In your banana. So most of your banana is potassium 39. A little bit more of it is potassium 41, and then just a tiny sliver is going to be potassium 40. So all of these numbers should add up here to 100% to equal the total mass represented of potassium in that atom. Okay, so we can determine the atomic mass of an element if we know its relative abundance in nature, those are the percentages, and the mass of those isotopes. So let's take a look at some example problems. We're going to go ahead and flip ahead to page 103. So if we look at page 103, we're trying to figure out what the an element is. We're given two different isotopes, and we want to know what element are these isotopes of. So they give you a little chart there. They tell you you have isotope 6 and isotope 7. They give you the mass of each of these isotopes in the chart, and they give you the percent abundance. How abundant is that in nature? So for the mass of isotope X6, we have a mass of 6.015 AMU. And for 7, we have 7.016 AMU. Now the relative abundance, isotope 6 here is not as abundant. It's in that 7.5%. And for 7, it's 92.5%. So what element are we looking at here? Well, we can figure out the atomic mass of this element by figuring out how much each of these isotopes contribute to the overall atomic mass. So how do we figure that out? Well, it's pretty straightforward here. You want to calculate the contribution of isotope 6's mass. So if I want to know the contribution that this isotope 6 makes, I have to take the mass and just multiply it by the percent abundance. So plug in my numbers. I've got 6.015 AMU times. Now I want to get this percent out of, I want to get it out of percent into a decimal. So to do that, if I had 7.5%, I divide it by 100, and that's going to give me 0.075. So when I multiply those two together, you get 0.451 AMU. So out of the atomic mass of this unknown element, 0.451 AMU is contributed by isotope 6. Now isotope 7, if we take a look at that one, its contribution, again, equal to the mass that that isotope has times its percent abundance, how common it is. Again, we got to get that percent out of a percent form and into a decimal, so you divide by 100. So if we've got 7.016 times 0.925, and this is AMU that we're talking about. So for this one, they tell you you're going to have 6.490 AMU. Okay, so now we know that isotope 7 contributes that much mass to our unknown elements, and isotope 6 is going to contribute this much mass to the unknown element. So how do we figure out what our element's actual mass is? We just add those together to find the atomic mass. So 0.451 plus 6.490 is going to give you 6.941 AMU. And then you go to the periodic table and you figure out who on the periodic table has this atomic mass, because it takes into consideration the weighted percentage of those isotopes, and it is lithium. So let's go back to our simulation here. Let's look at lithium. So lithium 7, that was one of our isotopes. Again, it has 7 mass, so 3 protons, 4 of those neutrons. If I add a neutron, it becomes unstable. But if I take away a neutron, lithium 6 is still stable, and it's about 7.59% of lithium 6 in nature in any given sample of lithium. So again, I hope that helps. There are a few more practice problems that you can practice on page 104, and I'm going to go ahead and post those solutions. So if you want to pause the video and practice the problems here, and then I will come back and show you the work for those practice problems. So hopefully this was helpful, and we'll see you in class on Wednesday. So here's the work and answer to number 15. Your answer was 10.81 AMU. I'm going to pause it now, and then I'll move on to number 16. Number 16, the answer was helium-4, because the atomic mass of helium is closer to 4 than 3. So there must be more helium-4 in the environment than helium-3. And number 17, I'll go ahead and go to next. And number 17, after calculating the atomic mass that each of these isotopes of magnesium contributes to the whole, we know that magnesium has an atomic mass of 24.31 AMU. Hope it was helpful, and thanks for listening.